Jadi sesuai sudah diberitahu, berikut adalah anggota-anggota kami, tadi di atas 6 orang dan juga satu pembimbing.
So the introduction of this research is corrosion is the degradation of metal due to electrochemical reaction with its environment, which can reduce mechanical properties, structural integrity, and surface life. Low carbon steel is highly susceptible to corrosion, contributing to around 30% of beton failures. Conventional methods like visual inspection and weight loss are destructive, time-consuming, and only provide post-damage information. The Arduino-based electrochemical corrosion rate detector monitors corrosion in real time. This system is more economical and simpler than conventional methods.
Okay, now moving on to the tools and materials that we use for this research. So our hardware centers around an ESP32 microcontroller and an LM358 operating amplifier to stabilize the data, and all of these components were integrated into one custom potential stat circuit. And for the electrochemical cell, we use 3 electrodes. Metal sample being tested being the working electrode, copper plate as the reference electrode, and carbon rod as the counter electrode. And for the electrolyte, to simulate the corrosive environment, we use a 3.5% natrium chloride solution, and also a pickling solution consists of 80-20 of distilled water and hydrochloric acid.
Okay, next.
And for the material preparation, first, the steel sample is treated using the pickling solution with the ratio of 80% aqueous and 20% hydrochloric acid. Meanwhile, for the other electrodes, which is the reference and counter, is sanded, polished, and cleaned before use. The electrolytes prepared are using the 3.5 natrium chloride, and we use the 3 electrode system configured in electrolyte solution. Before the testing, the potential stat system is assembled and calibrated before testing. For the overview of the system, we use an IoT-based electrochemical system for real-time corrosion. We integrate Arduino, which is an analog control, and ESP32 for data processing and IoT. We also use a potentiostat to measure corrosion signals from metal. We designed it to convert electrochemical reaction into quantitative corrosion rate data. For the design, our Arduino generates signals in PWM and reads response in ADC. The ESP32 processes data, logs results, and sends to web and cloud. The potentiostat circuits, which is configured in LM358 resistors and capacitors, converts small corrosion currents into voltage. We use the 3 electrode configuration, which is connected to the serial communication for synchronized operation, and the electrodes placed in a 3.5 natrium chloride solution to simulate marine condition. In our implementation, the system applies electrical signals to the electrochemical cell, which then produce an oxidation current, and then the potentiostat converts that current into voltage and then to digital data. Meanwhile, the ESP32 processes that data and calculates corrosion rate using Faraday-based equation, which is in millimeter per year. The results are then displayed in Microsoft Excel. This is for local monitoring. And then after that, transmitted to our web for real-time monitoring.
Okay, now for the results and discussion. First, we evaluated the potential accuracy by measuring the voltage results. So for the uncoded iron was measured at 0.60134, and it was slightly decreased after 1 day of immersion to 0.60078. But after 2 days of immersion, there's a significant drop. The voltage value drops to 0.5639, and indicating corrosion changes in the metal surface, but not really a lot of change in the beginning. But after 4 days, with the voltage falling to 0.15255, demonstrating that the longer immersion leads to greater electrochemical changes and material degradation, and also proving that our system can effectively detect and monitor the progression of corrosion.
As we can see, in all PRM measurements
argues that the higher RP or polarization resistance meant lower corrosion rate because RP is inversely related to I-core or corrosion current. And we can see that corrosion changed over time from active corrosion in the early stage to protective layer formation in the middle stage and partial degradation in the later stage. And we can see that after 2 days, the drop in I-core and corrosion rate created a stable passive layer which gave the best corrosion resistance, while the RP increased. And after 4 days, the I-core and the corrosion rate increased as the passive layer became unstable and corrosion became active again. As we can see, the RP decreased.
And for the last result and discussion, we test post-test analysis from corrosion rate based on safety limits from ISO or ISTM standards. If we see from the first data for non-corrosive iron, the corrosion rate is on 0.1266, which is if we see in the safety limits based on ISO or ISTM standards, it's classified as good. And for the second data, 1-day natrium chloride iron immersion, the corrosion rate is on 0.0903. When we see the safety limits from the ISO standards, it's classified as good. And the third data, 2-day natrium chloride iron immersion, and for the corrosion rate is on 0.0197. The safety limits based on ISO standards, it's classified as excellent. And for the last data is 4-day natrium chloride iron immersion. The corrosion rate is on 0.0221, and if we see the safety limits based on ISO standard, it's classified as good.
Okay, so the next one, we're going to talk about suggestions. Actually, when you're talking about our product, we have 4 main points about our suggestions. The first one is about the development of the software itself. We want to systematic software optimization by making our product into near cable, as well as using Bluetooth, as well as using internet for the connections of our product. The second one is multi-alloy detection range. As you know, right now in the current condition, our product focus on a low carbon steel. But in the future development, we hope that we're able to detect various metals such as aluminum and stainless steel. And the third one is autonomous material identification. Not only not show the corrosion rate, but we also hope that our product can test about how the difference in carbon within metal. And until the last one is the coating performance. Because to use our product, you need to make sure that the protective layer of the sample itself is clean before put inside into electrolyte solution. The next one, we're going to talk about conclusions. The LPR results. The system successfully recorded precise corrosion fluctuations. As you know, our product has effectively checked the corrosion rate, reaching day 1 at reactive state 0.12 mm per year, as well as reaching the maximum stability on day 2 due to the formations of the layer, the protective layer. Until at the last day, by day 4, the chloride ions began to compromise the surface protections and breaks the protections itself. And the second one is the Corlock technical architecture. The device utilized an Arduino Uno ESP32 as the primary IoT-enabled controller, supported by LM358, as well as the 3 electrodes, reference electrode, working electrode, as well as control electrode. We're able to get synchronize all the data monitored in real time through an integrated website by using the support of Microsoft Excel. Until the last one is the validation and industrial impact of our product. As you know, this recent proof that Corlock is a valid instrument capable of detecting real-time in electronic process changes, providing critical early detection solution to be able to make sure the safety in the environment of oil shore refinery. Okay, so the next one, we're going to talking about the validation and industrial impact. As you know, this research proved that Corlock is a valid instrument capable of detecting the corrosion rate as well as estimation long type of the sample itself, providing a critical early detections that helps a lot of oil refinery to prevent accidents in the corrosion itself. As you know, as you can see, we provide a solution to enhance operational safety and the maintenance cost efficiency for offshore oil and refinery infrastructure.
Okay, already finished. Okay,
Pas dulu nih mau tunjukin.
yes, how to use this instrument and proof
Apa mau pakai
indicator.
video aja, mau pakai video nanti
Corrosion
ini nih.
indicator.
Nanti ini mah datanya tuh di bentuk website. So how to use our product? First, after you open Microsoft Excel, make sure that the data is running and take a screenshot. And after that, you need to take the table, make sure that GH2 and GH3 is being captured. And after that, you need to open our website and put your data into the website. And you will get the estimated result.
Okay, the result is 0.0020,
Yes.
like this.
And it's classified as safe.
Okay.